We can go ahead and get this started then. We are going to continue our discussion of operating system implementation by looking at what normally appears in an operating system. There's a lot of variations on this. One of the things we didn't get to Monday it was, when I was discussing kinds of operating systems, is some of the specific focuses that some kinds of operating systems have. But we'll talk about that as we go through, so it's not a big deal. But you can see here we have users, applications, operating system, and computer hardware. Those invariably are the parts that are involved, and you can see where the operating system sort of fits into the picture there. Now, users are pretty obvious. They're people or perhaps other computer systems that want to solve some problem using the computer hardware. And you can see that there's a lot of steps in between the user and the hardware, because the hardware as it exists isn't useful for solving any problems unless you have software that actually implements a solution. And so you have users wanting to solve problems. Some operating systems only support one user at a time. I don't happen to have it right here on my desktop right now, but I have a cycling computer that has GPS built in, and it supports one user at a time because it's a cycling computer. I also have a Raspberry Pi on my desk, and that can support multiple users at a given time. So it really depends on the needs, whether or not you need to support multiple concurrent users. Some systems may have no users. And so you think about the computers that are in your car, because most cars have computer systems now that manage the fuel injection and the efficiency of the engine. It tends to be a very good way to create an energy efficient system that minimizes emissions. And most of the time that computer has no users unless there's a problem with your car, and then the mechanic becomes the user because they'll plug in the device that says what in the world is going on. So you have the user. They want to solve problems with the hardware. So we have applications which are specific solutions to the problems that users are interested in solving. Okay, and the application sits on top of the OS, no surprise there. There are special kinds of applications that sit directly on the hardware. It's difficult, it's challenging to write that kind of a program, but they definitely exist. Anybody who's worked with embedded systems would be familiar with applications that sit pretty much directly on the compute hardware. You do have some applications that are special. They're actually provided by the operating system itself. Some examples of this are things like your desktop user interface. And you can go through and have various menus, configurations, so that you can change how the display looks to suit your needs, install, uninstall applications. You may have command terminals. Those are the kinds of things that are part of the operating system, but they're actually applications. They're living outside of the OS proper, I might say. Okay, and then, of course, alongside OS applications, you also have user applications, and these are things we use every day. You have your text editor, you have your infernal blasted Zoom client, which we're all using now all the time. You might have a spreadsheet application, you may have a compiler. You'll be using compilers a lot, probably also VirtualBox. You'll be using a lot this term to run the virtual machine for CS124. So there's a lot of examples of applications that you use to solve specific problems. Okay. Now the OS itself may do a lot of different things, and not every operating system is going to do all the things that I'm about to tell you about. So you may have, for example, one of the most basic features is the ability to run programs. Because if I can support a general set of user applications, then I need to be able to load any one of those based on user request into memory so that that application starts running. So it's a very basic primitive facility. It's something you will actually get to build in the third project. So Pintos doesn't have that capacity by itself, and you will extend it greatly so that you can actually run user applications. Things like runtime linking. I'm not going to go into it right now, but it's a really cool feature, a way of having shared libraries so that the code that's common to all applications can be loaded into memory once and then integrated into an application that depends on it. There's a lot of features and facilities there. Okay, resource allocation. This is another obvious facility. You think about programs, number one resource that they use? Well, you may say memory, but it's in fact not memory, it's the CPU. And so the CPU has to be allocated across multiple programs that are in flight at any time. But memory is also a really great example because every program, as it executes, needs memory. And so you have these different kinds of resources that the operating system will allocate on behalf of running programs. Okay, so resources to manage, processors, main memory, file system, or external storage, and then other peripherals. I mentioned graphics memory is a really common example that you may not think of because every application sort of has its own area of the screen it needs to draw to. And you may have applications that are GPU aware, and the OS has to manage the application access to those resources. So you have file systems, and the operating system almost always has support for multiple file systems. I have all of these little flash drives, and so these are going to be some variant of the FAT file system almost always. You may have an ancient computer by now. It's hilarious that I say that, but an ancient computer that supports CD-ROM or DVD, and so there's a couple of file formats used for that. They're definitely not FAT. And then, of course, your built-in solid-state drives or maybe hard disks will have one of a number of file system formats as well. So lots of important details there. And you can imagine that the operating system is going to encapsulate all of those nuances and details so that you as a user don't really have to think about that stuff. Okay. Yeah, so as I say here on the slide, there are things that are even lower level than the file system stuff we talked about last time and this time. When you're interacting with the device from within an operating system, almost always you have to do reads and writes on ports. And you may alternately read and write to specific memory addresses that the device is available on. And we definitely don't want applications to do this. We even would like to keep parts of our operating system from having to do this. So if you have a file system implementation like, let's say, BetterFS, or you have a FAT implementation, and you'd like that implementation to be sort of device agnostic, then what you do is you start to encapsulate the interaction with the low-level device in this thing called a device driver, which I'm sure many of you have heard that term device driver before. And so that thing wraps the device, and storage devices, as an example, would typically be exposed as block devices. So you can say, hey, I want to read this block of memory from the device. Tell me when it's available. I want to write this block of data to the device at this location. And the device driver takes care of all the interacting with the hardware, which can be a pain in the butt. And you'll see this in PinTOS because PinTOS supports IDE, or I mentioned last time, it's also known as parallel ATA disk drives, which probably none of you have a computer that writes with parallel ATA anymore. I mean, at the very least, you have serial ATA that most devices are using. And then there's a bunch of other interfaces as well by now. But parallel ATA turns out to be simple, which is why PinTOS uses it. I've looked at writing a serial ATA or a more advanced disk controller layer for PinTOS, and I'm like, nah, it's way too complicated. Okay, so then besides the I/O services for talking to hardware, you have communication, which is for talking to, software talking to software or software talking to external systems. One of the most common examples of this is called inter-process communication, and it's abbreviated IPC. Anybody who does any extensive amount of systems programming is going to learn really well how to do inter-process communication, because almost always you want to have programs that can interact with other programs. It gives you a lot of flexibility and power, because if program A is talking to program B and program B dies, well, you just restart it and then reestablish the connection, and then off you go. And there's actually operating system architectures built around that concept. If you've heard of the term microkernel architectures, they're built around that notion, and so they rely very heavily on inter-process communication. Sometimes you have processes that need to talk to other computers, and so that's where networking would fit into the picture. And so you've probably heard of the networking stack, where the local computer has a MAC address, and typically we'll just pretend we're talking about Ethernet or Wi-Fi, and so there's mechanisms for routing messages from the local computer to other computers. Very exciting topic, but a little bit beyond the scope of CS124. Now, you also have accounting, and accounting is actually becoming increasingly important. I mentioned here, I think on the slide, systems that bill users based on CPU access time, storage, and networking. Now, this is becoming ubiquitous because of cloud computing. If I want to spin up a machine on AWS, I want to have a Google Compute Cloud instance or something like that, then obviously these companies provide those services for money, and so they need a way of actually recording what you're utilizing. And so you can imagine that accounting is a very central component of that. I mentioned on the slide that it's less common to bill for CPU time. And what I mean is your user is running some number of processes, and the amount of time your processes spend running is billed to you. Well, nowadays, you just spin up a whole virtual instance. That's a lot easier. So you don't really bill for CPU time in the same way as people did on mainframes. Storage, that's easy to bill for. Network transfer, pretty easy to bill for, because basically what the operating system does is log what was done, and then some external program can analyze those logs to determine, billing information and so forth. So accounting, extremely important nowadays. Then you have errors, and there's all kinds of errors that can occur. The very most obvious ones are when programs die in awful ways. They segfault or something like that, and you'll get to see a lot of that this upcoming term. In fact, you'll discover exciting new ways that your programs can fail, infinite loop, or go into all kinds of other crazy tailspins. So that's one of the exciting things about operating system implementation. But here's a bunch of other ones. Hard disk fills up. No surprise there. Everybody runs into this from time to time. File system is corrupt. So that's always an exciting one. There's just a lot of ways in which a computer can get into a situation where it can't fulfill the user's needs. And so the operating system has to have mechanisms for identifying and reporting this information in a way that's as graceful as possible. Okay, there are a few other ones. Some computing systems that are like high reliability will actually have multiple cores running in lockstep. That's the term for it. It's running in lockstep. So you're running the same instruction on two cores, and anytime the results don't match, you flag a fault saying an execution issue occurred. So this is where you're actually trying to verify that the hardware is working correctly. And you can imagine computer systems where the you need to be able to count those or identify those kinds of issues when they occur. Okay, abuses. So this is always fun. So you have various kinds of protection. You can imagine Windows, for example, has malicious code detection, and being a very, very popular operating system and a source of many different kinds of attack vectors. So Windows has built-in facilities for that. Many other operating systems do. I might mention Mac OS. I don't know how many of you are on Big Sur yet. I don't have the participant list up, so don't bother to say, yeah, I do. But just think about it. Mac OS, starting with a certain version of Catalina, started only allowing you to run code-signed applications, either from an identified developer or from an actual official party that had registered with Apple. So this is one of those things where they're taking a very strong preventative approach to application security. So this is becoming extremely common, especially since everybody is just downloading programs off the internet and running them. That's the standard way of delivering code now. And if you think about it, that should freak you the hell out. But fortunately, smart people are figuring out how to do that safely and securely for us all. Now, there's another aspect of this, which is that applications, you can see they're living up here in this applications box. And the fact that these are in different boxes is a clue. We'll talk more about this in a second. But there's a bunch of stuff the OS is managing on behalf of applications. And if apps were allowed to access this data and code directly, then clearly all kinds of mayhem would ensue. And a great example of this, the classic example, is DOS, Microsoft MS-DOS. And it was just a hotbed for computer viruses because any part of the operating system code could be managed or replaced. Any part of the data structures for the operating system could be affected. And I know I had tons of fun playing with that kind of stuff when I was a lot younger. Now you can't do that because we have computers that don't suck and we have operating systems that don't suck. So apps are not allowed to directly interact with all of that stuff anymore. What we have instead is this layer. It's a mechanism called system calls, which is the interface boundary between applications that need to do stuff and the OS, which does it on behalf of applications. So you can see that the OS becomes a trusted intermediary on behalf of applications trying to get work done. Now, the OS also has to protect processes from each other. You remember that I mentioned that when mainframes started supporting multiprocessing, which was the ability to run multiple programs at the same time, a big use case for those kinds of situations was financial data analysis. And so we needed to be able to protect running programs from accessing each other's memory. And this is another thing that modern operating systems have to do. We have to make sure that processes are protected from each other. And you might remember, I'm trying to remember now the names of these things. I can't believe I'm drawing a blank on it. I remember Rowhammer, I remember Heartbleed, but there was, Meltdown, and then there was another one. I can't remember what the other one was called. If somebody remembers, you can throw it in chat or just blurt it out. But these were basically issues with how the computer hardware works and that software could exploit so that you could actually get data out of other processes or out of the kernel. And that should freak everybody out because you may have one process that has your private SSH key that you're using, not zombie load. That must be a more recent one that I haven't checked out. But there was Meltdown, and then there was another one. I want to say Spectre. Does that ring a bell for people? One affected AMD, and another one affected Intel only. And yeah, I think it's Spectre. And these just happen to be, they're side channel attacks based on how the processor does speculative execution. One allowed a sandbox program within a process to get data from outside the sandbox, which is very common since we now have JavaScript and other scripting languages running inside of applications that also have sensitive data. And then the other one, Spectre, I think don't quote me on this. I have to go look it up. It's been a while. I'm a little embarrassed I don't remember this. But another one allowed the user applications to figure out information from kernel space, which is really scary. So anyway, but yeah, the OS has to figure out how to insulate processes from each other and from itself. And this is extremely important. Okay, so we're going to talk a little bit about computer hardware and how we implement these things. Okay. I hate to say it, but we have like 2 lectures that just goes over the x86 boot process. And some of it is kind of obsolete or anachronistic by now, but I still want you to see it because it kind of really illustrates the nature of how Baroque hardware can be. And like there's an address line on old PCs that they had to figure out how to enable and disable it. It will allow you to access memory above 1 megabyte. And the first computers didn't have enough motherboard space, and so they actually ran this address line through the keyboard controller. So you would talk to the keyboard controller to enable memory access above 1 megabyte. And because x86 has tried to retain backward compatibility all the way along, all of the computers since would emulate this behavior of routing the high address lines through the keyboard controller. And it's like, what is going on? What were they smoking when they designed this? Anyway, so we'll talk about that more in the future. But what I want to just talk about right now is how we provide these basic security capabilities in operating system implementation. There's 2 features that we desperately need. There turns out to be 3, but we'll talk about 2 right now. The first one is having multiple operating modes. As I say on the slide, the processor has different modes of execution that are physically constraining to the programs running on the processor. You cannot violate, or if you can, then the processor has a major security defect. So we'll just assume for the sake of sanity that you cannot violate these constraints through software. So the minimum requirement that you have is a protected mode that can do everything. We often call it kernel mode. And then a user mode that's greatly restricted. And there are some really important things that are disabled in user mode. Okay. So you'll hear this kind of terminology all the time, kernel mode and user mode, or protected or privileged mode as well. Now, this presents the question, what is the kernel of the OS? And I wish I could give you some sort of theoretically beautiful answer to the question of what is the kernel. The kernel is just the part of the OS that runs in kernel mode. That is literally the definition. It doesn't go any further than that. There may be other parts of the OS that don't run in kernel mode. They run in user mode. They're still part of the operating system. Think command shells. Think desktop environment. Think, depending on the operating system, you may have hypervisor capabilities so that you can run guest OSs. You may have device drivers running in other protection levels. The kernel is the thing that runs at the highest privilege level. Okay. Some processors have more than 2 operating modes. x86, I should say, starting, I believe it was with 386, was the first x86 processor that had multiple protection rings. Basically has had 4 protection levels for a long time. And I should say at least 4, because modern Intel x86 processors have a couple of additional ones for hypervisor capabilities. Like if you want to be able to run a hypervisor straight on the bare metal so that you can actually share compute hardware across multiple guest OSs really efficiently. And then there's even ones below that so that you can manage hypervisors, which is just like crazy. I'm not going to tell you anything about that right now because it kind of is a nightmare scenario, and it's pretty daunting what actually lives below ring 0 on x86. So i32 or x86-64 has 4 operating modes. Ring 0 is the kernel, and ring 3 is user mode, and ring 1 and ring 2 tend not to be used. The reason why they're called rings or hierarchical protection domains is because level 0 has all the capabilities of the enclosing rings. Level 1 has all the capabilities of the enclosing rings, and so forth. So level 3 is the least capable mode, but it's still perfectly adequate for writing applications. Okay. And you'll see this kind of thing in processors across the board. Like one of the things that I'm kind of excited about is I just got a brand new iPhone and I'm still setting it up, so I can't get any phone calls or anything. But ARM processors, I don't remember if iPhones are using ARM any longer because Apple is pretty much, they go their own way with their processors whenever they feel like it. But ARM processors, which are very common in many cellular phones, they have many protection levels. And you might say, well, why in the world do they have so many protection levels? Are they more secure because they have more protection levels? Well, the way to understand it is, what things can you do with the cell phone? What kinds of modes can it be in? I might be making a phone call. I might have the device just, like right now, this iPhone is inactive. Well, I mean, I suppose I can tell it to wake up, but while it's inactive, there's certain things that are allowed. While you're in a call, there's certain things that are allowed. If I'm running an application on the phone, there's certain things that are allowed. If I'm in a management mode where I'm installing an update, there's certain things that are allowed. So typically you'll have different protection modes for these different usage scenarios that allow things to be turned on and turned off. That's basically all there is to it. That's why you see so many different protection levels for something like a mobile device. Okay, hopefully that makes sense to everybody. If you have any questions, feel free to just plop them in the chat. Now, that's the first feature, is having multiple protection levels. And like I said, the real minimum requirement is just two, kernel and user mode. The other feature that you desperately need to build a secure operating system is this thing called virtual memory. And so this is the thing that I hope everybody feels reasonably comfortable with. And hopefully, as you make it through the term, you'll grow increasingly comfortable with it. Virtual memory is a central feature of modern processors for building secure operating systems. So the idea, as I have in this little picture down here, is you've got the CPU and you've got main memory over here on the right, and the addresses that are in instructions are virtual, not physical. They are translated through this thing called the memory management unit that I have right here, the MMU. And so you have an address translation that occurs so that the physical address may in fact be different than the virtual address. This gives you all kinds of benefits. The number one benefit is that all your programs can be compiled to have the same address layout because they're virtual addresses, and you can map those virtual addresses to different parts of the physical address space when you load the program to run. The other nice thing about it is that each program's address space can be completely isolated from every other program that's running. And so this is how we build process address space isolation. Virtual memory is so centrally important. So if you want to do yourself a favor to make 124 easier, every time you get a chance to look into virtual memory, take it and learn a little bit more about how it works, because that'll really help you. We will talk about it more specifically when we get into project 3 and 4, but especially project 4, because that's where you actually build the virtual memory system for Pintos. Okay, like I say on the slide, only the kernel can manipulate the memory management unit config. Makes sense, right? Because that, if user programs were allowed to manipulate the MMU config, then a process could just say, I want to see this other process's stuff, and then you can see it. So we don't want that, and so that capability is disallowed in user mode. Okay. All right. Yeah, we'll talk a lot about virtual memory, like why the hell do we want a TLB? Like, what is that thing? You don't even have to really think about TLBs, and you're really lucky we're not building a multi-core system, because multi-core, you have to start thinking about the translation look-aside buffers and all kinds of other stuff. Oh, it's a headache. Okay, so here is a standard memory layout for a program running in 32-bit Linux. You probably have seen me mention multiple times, we're on 32 bits. Irritatingly, we can't find 32-bit Linux distros easily, so I'm currently in the process of updating the virtual machine image we used last year so that it's got all the updates and patches applied so that we can just use it again, but it's 32-bit Mint Linux. But this is a standard layout for a 4 gig address space on 32-bit, okay? And as I say, all the processes have the identical memory layout, which makes it really easy to compile, link, and so forth. So they all start at this address, 804.8000 hex is where your program instructions start, okay? And the region where shared libraries are loaded is a specific address. And the kernel always lives above the 3 gigabyte boundary. Like all processes are laid out this way. The OS can just implement one memory layout for all processes, and that makes it a lot simpler. Okay. Now you'll also notice, like I say here, this is kernel virtual memory. So there's stuff that is for the process, but not accessible by the process that lives in this region of memory. So it belongs to the process, but the process itself can't touch it because it would just mess everything up. So this memory is marked only accessible by the kernel. And then you have the stuff that lives below the breakpoint for user versus kernel access. And the stuff below is accessible by the user process. And so we call those areas of memory kernel space and user space. It's pretty straightforward terminology here. And if user mode code tries to access kernel space, then you get a protection fault, okay? Shows up as a fault that you can handle in your operating system. Okay, yeah, so the OS keeps track of this memory layout for each process. You'll get to see this very detailed in projects 3, 4, yeah, especially 3 and 4, where you have to deal with this stuff quite a bit. And the process isn't allowed to access that information directly, okay? So you can start to see that the application has to ask the kernel to do things for it. The kernel takes care of it if it's a good request, and then the kernel responds, I've done it. Okay, now, any questions at this point? I'm gonna take a sip of coffee. We're gonna see an example of this interplay between user processes and the kernel in the context of console and file I/O, because that is going to be very useful for the first project, which is to write a command shell. So when you run a program on Windows or Unix, and remember that when I say Unix, I mean Mac OS, Linux, the Windows subsystem for Linux, whatever you decide to run your program in, it doesn't really matter. The OS sets certain things up for you automatically. You run your program. Anybody who's taken CS11 track or CS3 is very experienced with this because you get standard input and standard output, right? You write printf, it automatically shows up on the console. How does that happen? It's magic. You say scanf. Maybe you say scanf because you're scanning a string or something like that. But printf and scanf use standard input, standard output, or if you tell it, you can use the standard error stream as well. Okay. Now, the next question, which is very interesting, is, well, you have the standard input and output and error streams. Where can they come from, or where could they go to? If you're familiar with using Linux or Mac OS at the command prompt pretty heavily, then you can probably think of a number of places that standard input could come from and where standard output could go. So you might have the console. That's a pretty obvious one. You might have files. You know how you can say like program, and then you can say less than file, and it'll redirect the contents of that file into the program. You can do greater than some other file, and that'll take the output of the program. Now, the program doesn't know. The program doesn't care. It just uses printf, scanf, and the input and output are routed to the appropriate locations. You can also do this with multiple processes, and maybe some of you have constructed longer commands that are connected by pipes. So command 1, pipe, command 2, pipe, command 3. What you're doing there is saying, I want the output of this program to be routed into the input of the next program. The programs don't care. They just use printf, scanf, or whatever things, because remember that printf and scanf are implemented in terms of write and read. So you could just use write and read directly, or anything else that does, and all the input and output just shows up correctly. So you have read and write. I mentioned these. These are the signatures, and these are system calls, so that you know. You have to ask the kernel for information. You have to you say to the kernel, I have this information to share with others, and it takes care of it for you. So this is, in effect, this is process communication with the outside world. And so you attempt to read or write n byte. So you see size t. This is an unsigned. Typically nowadays, it's a 64-bit unsigned value. Although don't quote me on that. I can't remember if you need a flag to tell it to always be 64 bits. So let's see. Actual number of bytes read or written is returned by the function, and you'll notice that it's an S size t instead of a size t. That's the first S stands for signed, so it's a signed size t because errors are indicated by negative values. Okay, so end of file is indicated by 0. So you try to read, you're at end of file, you get back a 0. Invalid file descriptor. Your buffer pointer is, pointing into la la land, whatever. It's going to be a negative value. Okay, so the user program requests that the kernel reads or writes up to n bytes on behalf of the process. Okay. Now, these operations almost always take a lot of time. Let's say you're talking to a solid state drive. You're still talking microseconds, tens of microseconds. Let's say you're talking to the user. What if the user wandered off to get a coffee and a bagel? It could be hours, right? So read and write take some time. And so this also illustrates how almost always when these operations are performed, the kernel will context switch to another process that can make progress, okay? Almost always. System calls are very frequently points where context switches occur. Okay, file desc. This is a file descriptor. And as I say on the slide, it is a non-negative integer, so it can be 0 or larger, that represents a specific file or device. Now, you all know that programs can open multiple files, and the way that those are managed in Unix systems is that the files themselves are referenced by a number. And that number is simply the index into an array of file details that the kernel is keeping track of. Okay, so this is a simple example. We have 4 open files here whose file descriptors would be 0 through 3. And a given file's information would point to a little struct that says, here are the flags that govern the file, like is it read only, read write, write only. What's the current offset? So each process has its own offset into a given file, and then other stuff. And so, yeah, file desc is just an index into this array. Okay. Not every OS uses a simple array because you can also set the file descriptor limit to like 30,000, and it probably doesn't make sense to have an array of 30,000 elements. So you may want to have a hashing data structure or something like that. But you can think of it as being an array. And when you implement file descriptors in Pintos, most people use arrays because the number you have to support is low. It's like 128 or something. So they just use an array. Okay. So every process has this data structure, but you're not allowed to manipulate it directly. So this is something the kernel manages on behalf of the program. Okay. All right. Now, what's going on inside of this? I already mentioned that the user specifies these numbers. That's the file descriptor, and it's an index into this array, or you can think of it as being an index into the array. So the array points to, the elements of the array point to information relevant to that process. But there's also this additional thing that hangs off of it, which is sort of the kernel level, the global details about the file, which may be opened by multiple processes. And so you have this additional information here that is managed inside the kernel. Okay. And so this file ops thing is kind of your C version of virtual functions. So if you are familiar with C++ or Java or other languages that support dynamic dispatch and virtual methods and so forth, this is how it's implemented in a low-level kernel type abstraction. So you have file operations. You'll have inside this thing, how do I read? How do I read this thing? Because it may be a file, it may be a pipe, it may be a socket. So reading these different kinds of things will be implemented in different ways. How do I write it? How do I close it? Okay. So there's, function pointers that point to the, the appropriate implementation for that kind of file based on what kind of device it's on. So the kernel itself at the high level, like in the system call implementation, can do something very simple like this. So notice we look up in the files array. So we're at this first part. The user said they wanted to read or write on file descriptor 4. And so we just go and look up the entry for file descriptor 4. We get out, the next level pointer based on whatever it points to for file descriptor 4. And then we go to that thing's file ops and we tell it to do whatever read means for that thing. If it's a pipe, it might mean getting some stuff out of internal buffer. If it's a socket, it might involve talking to the network stack and seeing if packets have shown up and pull the data together so that the program can read it. Okay? Let me ask, does that make sense to everybody? Does anybody have any questions about this? It's a pretty important thing to understand. This kind of indirection is ubiquitous in operating system implementation. I don't think you'll have to do anything quite this sophisticated in Pintos, but I do hope at least that you understand generally how this is going on here. This is how we support common operations like reading, writing, closing, seeking on multiple kinds of file types. Let's just put it that way: sockets, pipes, and console and disk files. You can imagine something like a socket. If you try to seek on a socket, doesn't make any sense, or seek on a pipe. The implementation of seek would just return, I think it's like not impl or something like that. There's a particular error code saying this doesn't make sense for this kind of device. Okay, so we are able to have the same file open from multiple processes. So this is a simple example here where two different processes have the same file open. And you'll notice that each process has its own offset in the file that it is reading or writing to. Okay, so that's pretty typical kind of approach. Now, how do standard input, standard output, standard error come into being? It turns out that the way that Unix is implemented is that there's the kind of de facto standard that's emerged, which is that file descriptor 0 is always standard input, file descriptor 1 is always standard output, file descriptor 2 is always standard error. Now, the reality is this isn't changing, because if it changed, there's a ton of code and a ton of scripts out there that would just completely break if we ever changed which file descriptor was standard input. Nonetheless, I want all of you to practice good programming approaches, and there are definitions of these file descriptors. So you want to use standard in file no, standard out file no, standard error file no, so that your programs are not going to be broken if the definition of standard input, standard output, standard error ever changes. Okay, so just be aware that those things are there and you really should be using them. Okay. Yeah, and programs basically don't care about where standard input, standard output go as long as they work. So if you're writing a command shell, which all of you will have to do in the first assignment, you're going to need to be able to handle commands like this. grep is very common for searching through files, and you can see here I'm feeding a file into grep, and I'm looking for the lines in the log file that contain allow, the string allow, and I want to output the results to output.txt. So the command shell has to take care of setting up standard input and standard output for this program to run right before it is run, okay? So like I have on the slide, the shell sets grep standard in to read from logfile.txt and sets it standard out to write to the file output.txt. If it already exists, then it's truncated. You can do double greater than, and it will just append instead of truncating, but single greater than just truncates first. And so then once standard input and standard output are set up, then grep is invoked, okay? Now you have this weird thing, right? Hopefully you're all comfortable with C and C++ where you have argc and argv available on the arguments to main. And the way that this would be set up by the operating system is argc is 2 because grep has 2 arguments, grep and allow. argv has 3 elements because argv by definition or by the standard always has to end with a null entry. So you have grep, allow, and then null, okay? So generally you're going to see this kind of a sequence of steps inside of a command shell. You wait for a command to be entered, maybe using scanf to get a string, maybe using fgetS to pull a command into a buffer. Next thing you do is you tokenize it, so you parse the command, because remember you can have double quotes. Your shell doesn't have to support single quotes or backticks, but bash does, for example. You only have to support double quotes for tokens that include spaces. You don't have to even escape double quotes or anything like that. If the first token is an internal command, some commands are internal, so the shell implements them, then you go ahead and handle them. Otherwise, you fork a subprocess. So the command shell forks, and the parent process now has to wait for the child to terminate. The child process has to continue executing on. What it does is looks at the command to see if there are any IO redirection aspects. If there are, then the child process has to set up standard in and standard out, okay? Then the child process uses exec, or, there's like a family of functions to execute another program. You're asking the kernel to do it for you, okay? So you pass in tokens as the program's arguments. If exec returns, there was a failure, because exec is one of those functions that when it succeeds, it never returns. Instead, what happens is the process becomes a new program, and it starts running some other program. So exec only returns if file couldn't be found, there's a permissions error, some other horrible badness happened, exec returns. The child process just prints out there was an error and terminates, and then the command shell picks it up from there. Okay? Easy peasy, he says. All right, so that's basically how a command shell works. The question that I want to address really quickly at the end of this discussion is, how does the child process set up the standard input and standard output? Because remember, that has to be done by the operating system, okay? So when a process is forked, it is basically an identical copy of the parent process, except that it gets a new process ID, and the parent process ID is obviously the forking process, okay? So the child process has all the same files open as the parent process with the exact same file descriptors. I think I have a picture here. So you have your command shell, and it's got your standard input, standard output, standard error, and those point to various things. The child forks, And it gets copies of these little per process data structures, but they reference the same things. And the file descriptor array is also identical. So that's how your child process and your parent process share the console. If the child process outputs, it shows up on the console. The parent outputs, shows up on the console. You'll see plenty of this as you're figuring out your command shells. Now, if a command redirects, then you don't want the command shell doing it, because then you're effing up everything that comes afterward. And so you want that to happen in the child process, not in the parent. Okay, and hopefully that makes sense. So the parent process just waits for the child to do its thing, and then it prints another prompt. So the child process sets up standard input, standard output, and standard error. So let me show you quickly how this is done. There's dupe and there's dupe2. Dupe is not the one you care about. So you'll notice dupe duplicates a file descriptor, but you don't get to say what the target file descriptor is. So we're going to skip over this part because we're out of time anyway. Dupe2 is the one we care about because basically you can say what file descriptor you want to duplicate and where that file descriptor should be duplicated into. This allows you to replace standard output. This allows you to replace standard input or standard error. Okay? So you can read about the details here. Make sure you do, because you may run into issues if you don't follow all the semantics of these operations. But this would be an example of how, for example, you can replace standard output with some other file that you've opened. Okay, you just do dupe2 and the kernel takes care of it for you. Okay, and then you want to close it. I think I have one more example. We have grep allow, and then we're directing in logfile.txt and directing the output to output.txt. So after the command shell forks the child process can do these steps. We're leaving out the error handling, which you will have to do for the process or the project. So you have your input file descriptor, your output file descriptor. You open logfile.txt. You're opening it as read only because you're redirecting it in. You're not writing to it. Once you've opened that file descriptor, you dupe2 it into standard in and then close the input file descriptor. Standard in still has it open. Then you open output.txt. Notice you are going to create it if it doesn't exist or truncate it if it does exist and you're writing to it only. You dupe2 that file descriptor into standard out and then you close the output file descriptor, but it's still open through standard out. Okay? And so this is how you would set up the IO redirection for a command before executing. The last thing you would do is call execve or one of its variants to invoke grep. And if it doesn't come back, you succeeded. Okay. Sorry that was rushed at the end. What we're going to talk about next time is various architectural approaches. I mentioned microkernel architectures. We'll talk about that and many other kinds of architectures starting next time. If you have any questions, I'll hang out in the Zoom call. Otherwise, I'll see you Friday.